Thank you, and hello everyone. My name is Chris Cohn from Minter, a Siemens business, and it's my privilege to kick off this webinar on Photonics IC design, featuring Luceda IPKISS.EDA and Tanner EDA tools. Joining me later will be Ruping Kao from Luceda Photonics, and she'll be covering the Luceda IPKISS toolset along with a demonstration. So let's get started. So on the Minter side, Tanner EDA provides a complete analog, RF, mixed signal, and digital IC design solution from design entry to simulation to physical layout and verification, all the way through tape out. We also work with a company called SoftMIMS to provide a MEMS IC and design modeling flow. Pictured here are some of our solutions in the IoT space, including in the areas of power management, MEMS, and biomedical. With usage by companies listed here: Second Sight, NeuroPace, Proteus, and Knowles. And in particular, FLIR has been using Tanner tools for their thermal imagers, and all imaging chips, or all imager chips on both generations of the Mars rovers, were designed using Tanner tools. And then addressing the Photonic IC design solution space, Minter has been teaming with Luceda Photonics for the past couple of years to combine the power of Luceda's IPKISS tools with Tanner's intuitive graphical environment. So along with supporting the latest capabilities to enable an EDA, or rather EPDA, based PDK-driven photonic circuit design environment, Luceda's IPKISS tools provide a powerful Python scripting environment to develop, analyze, and model novel components to augment your PDK. In the traditional CMOS design space, Minter has a large cache of materials and examples to guide you through various aspects of CMOS IC design, and these are available at www.minter.com/TannerEDA. You can find white papers and webinars on CMOS-based design, and there's even a virtual lab to enable you to test drive Tanner tools in a real-world setup. And actually, for the past few years, Tanner, together with the Calibre team and other product teams at Minter, have been partnering with Photonics and MEMS tool providers to provide IoT solutions. Starting with MEMS, Tanner has a long-standing relationship with SoftMIMS. And then in the Photonics space, we, in addition to Luceda Photonics, Minter is working with Lumerical Solutions, Phoenix Software, and VPI Photonics. So this is the Photonic IC design framework and design flow we are building. So looking up at the top over here on the left, we have design capture, and this is implemented, or I guess performed using Tanner SEdit. We have upcoming OA native support in our v17.2 release. This should be in summer of 2017. It also supports a Photonic schematic driven layout, and it supports simulation of both pre and post layout. Next, we have layout implementation, and this is done using LEdit, or Tanner LEdit. And this has a seamless interface to IPKISS to provide photonic P-cell capability, waveguide generation, and layout direct simulation. So both SEdit and LEdit, these are going to be inside of the native open access design environment. And here, Minter has comprehensive open access PDK support to enable PDK development and QA. And it also serves as a framework for future open access based plugins through the Open Access API. Then on the simulation side, Tanner EDA supports both the Eldo platform and Tanner T-Spice, and these are both capable of running simulations using Verilog A models, and this is ideal for performing photonic simulations inside of a kind of a system level application. And then on the photonic simulation side, we currently support the Luceda Cafe simulator, and we anticipate additional photonic partner simulation capabilities in the future. So stay tuned for announcements here. And then finally, enabling true scalability is the Calibre verification platform. Calibre is the dominant tool for physical verification, and Tanner supports all of its available design and verification products, and it has a common interface to both the Calibre RVE and Calibre Interactive GUIs. So just to talk about the MEMS environment. So together with soft MEMS, Tanner provides a complete MEMS design and modeling software package. And the key to this, and what's really helpful in addressing a lot of photonics IC design, is built-in support for curvilinear shapes and T-cells with dynamic scripting capability. So this includes enhanced Boolean operations, and these are used to generate some of the structures you see on the slide in front of you. And there's plenty of information available on this, and I'll refer you to go online to find more information on the MEMS flow. And then this leads us into talking about Tanner LEdit. This is really the starting point when talking about Tanner EDA tools. Tanner LEdit IC is an easy-to-use, easy-to-install, programmable physical layout engine with true curvilinear support. It's programmable via C or C++ or through Tcl. It supports parameterized layout generators. There's also full EDA flow support, including the ability to be PDK driven or IPDK driven. It has or supports multi-user, multi-libraries in a single project. There's design hierarchy, or it's design hierarchy capable with a navigator to allow you to browse through your design, and it supports all Calibre verification tools. In addition, there's a number of rich productivity features, and not all of them are listed here, but some of my favorites are object snapping and node highlighting. And then again, the Tanner LEdit tool is already in the open access native, or is an open access native database, and it supports open access, and we even created the initial Luceda IPKISS.EDA integration through the open access API. Next, let's talk about the schematic capture tool. So this complements LEdit. It performs schematic capture for doing simulation and driving a schematic-driven layout. It supports multiple views per cell, including a schematic, a symbol, SPICE, or Verilog or Verilog A. And then there's full, again, like LEdit, there's full EDA flow support, including PDKs and IPDKs. It supports multiple users and multiple libraries. Here you can already import open access or EDIF, and again, the Tanner SEdit tool will be open access native in the v17.2 release, available summer of this year. It's design hierarchy capable with a navigator to help you browse through your designs. There's the capability to do schematic checks, and it also supports Minter's Eldo and Tanner T-Spice tools. I think we covered that already. And then again, looking for other simulation solutions, there's a capability to add third-party simulation solutions. So stay tuned for follow-up webinars where we'll highlight this capability in the future. And this is really how you drive a schematic-driven layout. So here's an example schematic. When you perform STL, you'll it automatically places devices with the correct orientation and relative to each other. Then you can do initial routing. Here's the automatic waveguide routing, and then converting to waveguides using the IPKISS tool suite. And it finally finishes off the electrical routing using multiple levels, and it's multi-level aware and with automatic via insertion. So now let's go ahead and discuss the IPKISS, or introduce the IPKISS.EDA tools. So here, shortly, I'll hand it over to Ruping Kao to talk about the IPKISS environment. But just briefly, you can use IPKISS in an established EDA environment, and that's using the LEdit tool. This enables you to drag and drop components from your parameterized PDKs and libraries. You can create hierarchical cells inside of LEdit, connect your components together intuitively, and you'll see that in the demonstration. And then you can run and debug DRC inside of LEdit using Calibre Interactive and Calibre RVE. And essentially, you get to use all the power available inside of the Python-driven IPKISS flow. So Ruping, I'll go ahead and hand it over to you and allow you to go into more detail regarding the IPKISS design framework.
Okay, thank you, Chris. This is Ruping from Luceda Photonics. I'm going to introduce you the IPKISS design framework, and after which Chris will give a wrap-up at the end. So IPKISS started off more than 10 years ago as a specialized tool to draw mask layout for integrated photonics designs. And now, as Chris just introduced, it develops into a full design framework. All the design steps, including component and circuit level layout, physical and circuit level simulations, are consolidated in a single flow. IPKISS allows users to move back and forth through the flow smoothly without compromising efficiency or reliability. So this flower-like picture shows how a photonics designer realized a design using IPKISS. We first define a building block or a component, like an MZI or Mach-Zehnder interferometer. We define the various views associated with this component. So first, we define the component geometrically as its layout view. Then its 3D geometry, or the virtual fabrication view, is calculated based on the layout and the process information. Next, this 3D view is used to create the physical model of the component. From this result, a compact model can be derived as well for circuit simulation later on. These are the flow performed by a component designer. They design and optimize the component by looping over these steps in a fully automated way. Once the component design is done, circuit designer may use these building blocks and put them into a larger circuit. So first, we define the circuit by logical connectivity between the components, and a circuit model is automatically created based on the compact models of the individual components. Next, a circuit simulation can already be carried out to verify if our design behaves as expected. Then, we specify the component instance, location or rotation on the layout, and the circuit layout is generated in a semi-automatic way. A post-layout simulation can be performed, which takes into account layout effects like interconnecting waveguides. Finally, after the chip is fabricated and tested, the measurement results can be used to calibrate the circuit simulation model used for the next design cycle. A circuit designer may focus on these last 4 steps, and with all of these, we close the entire design loop. In IPKISS, Python is used as the primary language to script the design. With its many advantages, like it has a large engineering library available for use. Scripting has made many of the design tasks easier and scalable, from defining a photonics component, sweeping over design parameters, to optimizing a design. As photonics technology matures, there are more designers specialized in circuit or system level engineering, and an EDA-like design environment is more and more demanded. To answer to that, IPKISS has been collaborating with the Tanner tools to integrate its photonics design knowledge into the EDA context. Specifically, the photonics designer can use LEdit, Tanner's layout editor, to visually lay out the photonics circuit, together with IPKISS engine running in the background. We will show such a flow towards the end of this talk. IPKISS fully supports PDK, or Process Design Kit-based design flow. Photonics designer can use the PDK like the electronics designers do. For example, they may use directly the building blocks or components from a PDK to compose a circuit. Everything they need, including the component layout, the component pins for defining connectivity, as well as the simulation model, are available in the PDK. Currently, we are collaborating with the major silicon photonics foundries to provide PDK like IMEC, IME, IHP, VTT, and also packaging foundries like Tyndall. As we've mentioned, as a circuit or system designer, the main task is to use existing components from the PDK to compose a larger design. Here we show the major steps in this flow supported by IPKISS and tenor LED integration. The Photonics P-cells from the PDK or those ones created within IPKISS are available as LED design library. This is made possible through the open access standard. Designers can drag and drop their P-cells, route optical waveguides between them, as well as perform electrical routings like how they're used to in LED. After the circuit is made, it must be verified against the functional specifications you have in mind, as well as the manufacturability requirements imposed by the foundry. CAFE is the compact model simulator integrated within IPKISS. Because it's based on S-parameter model, it's suited for larger circuit or system simulation, and verify if your circuit functions as intended. For manufacturability validation, it's now possible to call Calibre DRC directly from the tenor LED interface. DRC results will be interactively shown in the LED environment. So that summarizes a circuit designer's flow. For component designers who supply the building blocks, IPKISS offers the following features, as we briefly mentioned at the beginning. So component layout is created as parametric cell or P-cells and is written in Python. In IPKISS, there's already a large template library of Photonics P-cells that are technology agnostic and free to use. And again, the component definition includes all the aspects or views that may be used in the entire design flow, including layout, logical interface, netlist, compact model, electromagnetic or EM simulation settings, etc. For EM simulation, the built-in simulators from Luceda includes Comfa, the 2D EME or Eigenmode expansion solver, REMIC, the 3D EME solver, and specific solvers for Scalability and AWG or shell slab regions. We also provide, and our users have also customized themselves, the software links between third-party simulators from CST Studio, Lumerical, etc. Component design exploration and optimization is also possible and made easy. Layout parameter sweep is done very efficiently because of the fact that component design is parameterized. And IPKISS provides so-called containers which creates P-cells that contains other P-cells. For example, a range of ring resonator designs, each is connected to an input and output grating cupola that are spaced in a way according to the testing instrument. Fast component optimization is also possible. The parameterized component layout has its associated simulation model. IPKISS interfaces with EME or FDTD solver. It enables a fully automated flow where the device performance can be optimized by refining device layout according to simulation results. Here's a paper showing one of the examples. For an MMI design, here the author gives an initial layout design, specify the target performance metrics to be optimized, and a set of layout parameters as optimizing parameters. The flow results in an optimized design of this MMI. The result shows that the chance of finding out the best device is the highest comparing to the other methods, and it's the most efficient. A good demonstration of all the previously mentioned features is the filter toolbox, and specifically the AWG Designer. It's built based on the IPKISS infrastructure. Luceda will release this product very soon. AWG, or Arrayed Waveguide Gratings, is a photonic device that are commonly used for WDM applications. It's known as very hard to design because there are many design parameters that are intercorrelated, and they are affecting how the device works. With IPKISS, devices are defined as P-cells with associated layout and simulation model, and we are able to build the toolbox that makes designing such a device much easier, while designers still have the control over all the details of the design. The filter toolbox fills the gap between the functional specifications and the layout design parameters. What has been taking an even experienced designer months of work, all this knowledge is consolidated into a single toolbox. Designers may simply enter high-level specs like peak wavelength, FSR, and number of output channels. Then an AWG design is automatically computed, including how the waveguide arms are drawn, their length, the length between them, how the free propagation slab and the aperture are drawn, etc. This computation is done in a matter of few seconds. The design is adaptable to multiple fabs. The design algorithm is also made DRC aware. For example, we have made DRC clean sample designs on the IMEC technology. Of course, experienced designers may still want to have control over the design details. Design parameters are made available for them to fine-tune the AWG performance. For example, designers can customize the number of grating arms, waveguide width, band radius, aperture type, output aperture spacing, star cupola grating period, number of dummy apertures, etc., which will affect device performance like the insertion loss, crosstalk, intraband and out-of-band ripple, roll-off, etc. In summary, AWG design has never been made as straightforward and efficient as by using the filter toolbox. AWG mask layout is automatically computed in such a way that it meets with the system specs, and in the meantime, all the key design parameters are accessible to the designers. For computing of the AWG design, I will not go into the details, but only briefly mentioning that different methods that have been used to calculate the different parts of the AWG design. The device is decomposed into a sub-circuit of an output and an input star cupola connected by an array of waveguide delay lines. For the star cupola device, 3 parts are simulated with different physical solvers. The free propagation part is applied with Fresnel diffraction model. The input and output aperture are solved by eigenmode propagation or FDTD. From the designer's perspective, changing one of the design parameter, for example, the waveguide geometry or the number of waveguide arms, results directly in a change of simulation results of the entire device. All the middle steps are taken care of by the filter toolbox. Like all the IPKISS P-cells, the generated AWG component is associated with different views for use in simulation and layout. It has a simulation model which can be used for functional validation of the circuit. It has the layout view, of course, which can be exported to LEdit. And next, I will show a demo of how to place and route an AWG component into a larger circuit within LEdit. So this is the LEdit user interface. First, we open a project. Choose the top level library. And here's a multiplexing circuit that we'd like to lay out in this demo. So in the LEdit user interface, we have IPKISS-based PDK content available, including the technology layer settings and design libraries. Here we demonstrate with a DemoLib PDK, which is technology agnostic and is intended for demo purpose. And we also have the design library that we have exported, which contains the AWG design we have done with the filter toolbox in IPKISS. To start designing, we create a new cell first. From the design library, we first instantiate a modulated P cell. So we'd like to duplicate this P cell by 4 times. Now I'm grouping them together so that we can align them easier later. Now we're dragging our AWG. Rotate it to the correct position, flip it, and make a copy of that by Ctrl C and Ctrl V easily. And align the two AWG vertically. Now I select the 4 modulators and the 2 AWGs and distribute them horizontally. Now we add the edge coupler P cell, which acts as the fiber to waveguide interface. Rotate it, make a copy of that. Also align them vertically. Give it a certain space between the horizontal direction. Group them as well. And align it horizontally with the modulator group. Okay. Now we have placed all the components we need and we will connect them together. We select the silicon trace layer, which is the assisting layer that is used to draw guidelines to generate the actual waveguide for the mask. Now we activate the wiring tool and start to connect the device together. Okay, we basically use the mouse click to go from one port to another, which the trace is snapped onto. Once the trays are finished, we need to convert it into the real waveguide. We go to the Luceda menu button, select Waveguide, Generate all waveguide. So following the trace line, the waveguide with the desired waveguide core, cladding, process, and geometry is generated. It is automatically matched with the waveguide types and the component ports. Smooth bending structure are automatically generated as well, and you can always parameterize it as these generated waveguide routings are also P cells. So here we are finished with the multiplexing circuit layout, and we save it. Next, we will perform DRC or design rule checking on this design. In an edit interface, we can call Calibre DRC directly. We click on the Run button in the toolbar. That opens the Calibre interactive window on the Linux machine. Here you can customize your Calibre run like you are used to, or here we just take all the default and start run. As we have a simple test case, the run is done in no moment, and we found one violation that we intentionally put on the design for demonstration purpose. We highlight the spacing violation result, and you may see the highlight marker indirectly shown in LED window. To correct this error, we move one of the waveguide trace layer apart from the other. Regenerate the actual waveguide with keyboard shortcuts, and you may see the updated layout. Now we rerun DRC on the new layout, and there's no more error. With that, we have demonstrated how we realize a DRC clean AWG circuit layout with LEDit and IPKISS. Prior to the AWG component layout ready for use in circuit design, which we demonstrated just now, we used our Photo Toolbox to design and simulate the component. Recall that the simulation of such an AWG is based on the compact model with a series of star cupola and arid waveguide. The simulation result meets quite well with the actual measurement results, as you might find out in this paper as one of the examples. It's a 12-channel AWG with MMI-shaped aperture fabricated on the IMEC technology. This compact modeling is also suited for simulation in a circuit context for its good accuracy and simulation efficiency. In the previous demo, we have laid out the circuit and have ensured its manufacturability by DRC checking. However, we are not confident if the circuit performs as desired. So in the next demo, we will show how we drive the cafe simulation, which is IPKISS compact model simulator, from the circuit layout we have just created in order to verify its functionality. So here, we will use a simpler circuit of an 1x8 AWG, of which input and output channels are connected by grating cupolas. To set up the cafe simulation run, we go to the Luceda button in the menu bar and select Start Notebook Server. This is not yet our ideal flow, and we are working on the integration with Tenors S-Edit to drive cafe simulation directly from there. So here, in the web browser, you see the notebook interface where the simulation is configured in Python language. It includes IPKISS script to import the process and layout information from LEDit, the test bench setup for cafe simulation, and the results plot settings. So we go ahead and run all the code blocks. We see that they are executed by consequence. The first results we see is the AWG circuit layout, which indicates that the layout is correctly loaded for the simulation. Next, we see the cafe simulation is running, and we got the result. On the right is the transmission spectrum for the AWG component alone, and on the left is for the full circuit. You may notice that the extra loss introduced by the waveguide and the grating cupolas, as in here, as indicated by the peak height and the ripple. So that concludes the entire back-end design flow for Photonic circuit layout design, showing how to implement a circuit layout with LEDit and IPKISS, perform DRC with Calibre, and perform circuit functional validation with IPKISS Cafe. So now I'll hand back to Chris to wrap up this session.
Thank you, Ruping. Before we wrap up this Photonics IC design webinar, let's say a few words about physical design verification. And to kick that off, let's talk about Tanner Calibre 1. The Tanner Calibre 1 package allows you to run Calibre nanometer DRC and nanometer LVS directly from LEDit using embedded icons on the toolbar, and you saw that in the demonstration from Ruping. And then from there, you can use Calibre RVE to actually view Calibre DRC, LVS, and PEX results and highlight them in both LEdit and SEdit. This supports highlighting of nets and devices with cross-probing, and this is all key to supporting a Foundry-qualified sign-off flow. And then more particularly about verification in silicon photonics, one of the key issues that you'll see in when doing physical verification with silicon photonic structures is a large number of false errors that occur. And so the Calibre toolset has a capability to reduce false errors using something called equation-based DRCs. This is where the Calibre engine uses geometrical information and applies continuous functions to perform multidimensional physical verification analysis. And when you apply that, there's a huge benefit to where you can go in and reduce the overall number of false DRC errors, and you can actually view the errors that matter. And so this enables faster debug and error annotation. You can do checks that actually weren't capable before without these equation-based DRCs. There's reduced design variability, simpler, smaller decks and checks, and this is all coming from the capable that is already available inside of the Calibre package. Okay. And then on the Photonics LVS side, the Calibre nanometer LVS tool has the ability to extract devices and device parameters from components that were created using curvilinear structures. So you can extract things like your radius, your gap distances, your gap coupling lengths, and a number of parameterized factors such as that. And this enables extraction and careful validation of that's often required on these non-traditional constructs. So one of the key things that you may be interested in is your minimum radius of curvature. And then on waveguides themselves, you'll want to be able to extract the width, the total path length, or in a lot of cases, you'll need to extract the actual waveguide type, which may be a composite of several layers. And in a lot of cases, these properties are context dependent, and Calibre supports that. And then you really can't talk about doing a physical verification in silicon photonics without talking about your lithography impacts. And most people who have actually done component design for in silicon photonics have seen that what they actually manufacture and then measure on the bench will give them wildly different results than what they'll simulate if they only simulate the drawn physical geometries. And so the Calibre lithography simulation capability enables you to capture the as-manufactured structures. And we recommend using this capability to complete your litho-aware device characterization. So this would include the Calibre lithographic simulation and a link to a solver such as the Lumerical FDTD Solutions simulator to improve your overall flow. And then finally, I want to talk about some of our upcoming events. Coming up this month, rather quickly in Xiamen, China, on May 21st till May 25th, there's the integrated photonics training that's supported by Luceda Photonics. Here's a link in case you want to join that. And then we'd like to invite you to join us in Berlin, Germany on October 22nd for the half-day workshop. That's going to be the half-day workshop the day before the actual beginning of the Group 4 conference. And here, Mentor and Luceda Photonics will be teaming up with Lumerical Solutions, and will provide a workshop that's centered on Mentor's easy-to-use, easy-to-install Tanner EDA tools with the IPKISS interface, along with the Cafe Photonic Simulator. And we'll feature integrations to the Lumerical FDTD Solutions Simulator, along with Lumerical's Interconnect Photonic Simulator. So there's a link here, and this really highlights the framework of our open access-based photonics flow available from Mentor using the Tanner tools. Just one more note about that. If you are planning to attend the Group 4 Photonics and the workshop, we recommend you register early. Unfortunately, there's only seats for 100 people to attend, And so the first 100 will get to join, and after that, we'll just have to figure out another way to follow up with you guys. And then finally, we have ECOC 2017 coming up in September. This will be in Gothenburg, Sweden. And please come visit us at the Luceda Photonics booth. So let's go ahead and conclude the webinar. So I just want to highlight that we've shown Minter's easy to use, easy to install Tanner EDA tools. And this is the common framework that we have addressing just general IoT design. And we have an analog mixed signal with RF capability and digital capability, IC design flow to address traditional CMOS design. There's also MEMS design and modeling with built-in curve-in support or curvilinear support. And we're addressing photonic IC design through our key partnerships. And right now we have a solution to enable you to perform photonics IC design together with Luceda IPKISS EDA and Tanner EDA tools. And this provides a full framework enabling photonic design to meet today's needs. It also supports PDK-driven photonic circuit design. It also supports photonic component design, including an AWG design methodology available through IPKISS. And as always, the Luceda IPKISS engine is extensible using Python scripting. So thank you very much for joining us for this webinar. And please stay tuned for updates from both Minter and Luceda. And I guess I'll pause it now and enable us to take further questions.